Yeah, we'll do a couple different things. Jerry Dickens was going to do some of this, and he couldn't come because I guess he hurt his back. So we'll try to segue from one end to the other here. And want to think about some other aspects, including a couple things we touched on this morning. So here are our sources of CO2 to the surface environment. We've got arcs we talked about, right? We all believe that to be true. Mid-ocean ridges are another one. Oxidation of organic carbon, it's usually not this spectacular, but you have outcrop and that weathers, and so there's organic carbon in there and fluids. And these are this is a combination side-scan sonar and seismic and artistic rendition of part of the North Sea off the coast of Norway, where you've got a lot of methane venting to the Earth's surface out of sedimentary basins. That turns out to be interesting. And this is a site of hot spring degassing along the main central thrust in Nepal, where we got metamorphic carbon produced by thermal decomposition reactions down at 10 or 15 kilometers coming to the surface. So these are kind of what we think of as the sources of CO2 to the surface environment. And I just want to get a little theme here. We talked a little bit about how arc weathering was important, or at least I think so. And of course, arcs are a source of CO2. Mid-ocean ridge, a lot of volcanism there, source of CO2. We'll show that alteration of the oceanic crust, which you mentioned before, is a sink for CO2. So source and sink are there, source and sink are there. Turns out that in the Himalaya, we've got a source and sink as well. We talked about the weathering sink a little bit in the Himalaya, and I don't want to give you the impression that it was trivial as zero, just that it wasn't anomalous the way that hugely anomalous the way that people thought it was. And here's a map, sketch map of the geology of the central Himalaya. There's Kathmandu there. This is in central Nepal. This is the Annapurna Massif up here. This would be the Dhaulagiri Massif, Manaslu. These are big 8,000-meter peaks through there. And the lesser Himalaya are in white, and they're overridden by the high Himalayan crystalline gneisses along the main central thrust shear zone, this thing marked as a thrust fault. It's really a ductile shear zone. It's not a fault that you can go and stick your hand on. It's an exhumed ductile shear zone. And then we have Tethyan sediments that are separated by normal fault up at the top. And those stars are the locations of some of the hot springs, and they're mostly located near the main central thrust and in the bottom of the major river valleys. There's also a graben structure up here going up the Kali Gandaki. And they're all along the Himalayan front. There's a paper from the Journal of Geological Society of India in 1870 about the hot springs of India. And they were cataloged, several hundred of them, and Nepal wasn't part of British India, so they didn't even count that. So it turns out they're interesting for a couple reasons, but for our present purposes, and here, is that a little bit too dark? Yeah, that's all right. All right, here's a Google Earth image of, this is the Annapurna Massif there, that's Machu Picchu, the famous fishtail peak. And this gives you, it's exaggerated, but it gives you an idea of how incredibly deep these gorges are. Just on the other side of Annapurna there is a gorge between Annapurna at 8,000 meters and Dhaulagiri at 8,000 meters, and the gorge goes down to below 2,000 meters. So this is the greatest relief you see on the planet, and it's quite spectacular. And the hot springs are generally down near the MCT, which cuts through here, where the topography steepens up substantially. This is, even without vertical exaggeration, this is really steep. And it's a cool place to go, though. I highly recommend hiking up, doing the Annapurna Base Camp trek, which you go up there when you come out there. And it's actually not that bad. I did it with my 7-year-old a few years ago. So, of course, there were a lot of middle-aged and 20-something tourists gasping by the side of the trail, and she'd kind of motor past them, but she's that kind of kid. And so anyway, we've got this incredible topographic thing here, and so we've got these geothermal systems. And there's a big story about them, but it turns out both for heat flow, they're very efficient at getting heat out of the system. But it turns out some of them, they have lots of, this is travertine, calcium carbonate, and this is CO2 bubbling out there, right? PCO2 exceeds 1 atmosphere right there, right? Even, we're up high, but not that high. And the temperature, that's like 55 degrees. And the temperatures of these springs range, in some cases, up to 90-plus degrees centigrade. And they boil in India because that's the boiling point at 4,000 meters. This is only at about maybe a couple thousand meters here, something like that. So anyway, that CO2, it turns out, we've done lots of work on this. I won't go into the details now. But it's being produced by decarbonation reactions, these lesser Himalaya going down 10 or 15 kilometers depth, where there are metasedimentary rocks, including carbonates. And it's being cooked off, generating CO2. Calcium carbonate reacts with silicate rocks to make calc silicates like amphiboles. and free CO2. And we see fluid inclusions with a high CO2 fluid in them and all that kind of stuff, and it comes out. The reason doesn't look like much, right? But when you actually, there's a whole bunch of work that goes into this. When you look at the calculation, the amount of CO2 being consumed in central Nepal, in the Narayani watershed, which is about 30,000 square kilometers, occupies about 200 kilometers of strike length along the Himalayan front. And we have a chemical weathering rate for that. Like I said, it's not zero. There's definitely weathering going on. But it turns out that the amount of CO2 coming out from metamorphism exceeds significantly the amount of CO2 being taken up by weathering. Okay? This is true for central Nepal. We're working currently on areas, this is very high exhumation rate. You saw the topography. It's dramatic. Right? And we're working in a couple of other areas of the Himalayan front which have still high exhumation rates, but not as high, in Bhutan and in northwest India. And there, we also have a lot of heat flow associated with the geothermal systems. We have a little bit less CO2 coming, somewhat less CO2 coming out, probably because of the local variation in lithology of the lesser Himalaya. So we're trying to get a better estimate of what an appropriate value would be for the Himalaya as a whole. But in any case, the fact that metamorphism is releasing CO2 as weathering is taking it up is another one of these kind of balancing acts. And I think here we've got more going out than going in. So the Himalaya are a net source of CO2, completely opposite what everybody's been saying for 30 years, right? But I suspect what we'll find in the long run is that this does, range-wide, these springs don't fully balance the uptake, but they balance a significant part of it. So it's interesting that one way to help keeping CO2 on track is if your sources and sinks are strongly coupled. Arcs produce CO2, arcs suck up CO2. Himalayas produce CO2, Himalayas suck up CO2. The mid-ocean ridge produces CO2, mid-ocean ridge sucks up CO2. It's not obvious that those have to be perfectly in balance, right? But the fact that we're seeing this makes you think, right? So this is an interesting point that I thought I'd take a minute on. And it's all kind of, it's a fun place to, there's all kind of cool stuff there. All right, sinks of CO2. Weathering, we talked about. There's some silicate weathering there, core stone. We've got carbonate weathering. We mentioned that. That's karst topography and along the coast in Portugal. Did you ask me a question? Oh, okay. So once the weathering products, the calcium and magnesium primarily, get to the ocean, they make guys like this. All right, that's a foraminifera, a coccolithophorid algae. It makes calcium carbonate, and that's actually a bloom of coccoliths in the North Atlantic in the spring. You can see from space, and so they take up CO2 and they sink it out. And then we also have the burial of carbon as organic matter. Here's a New Albany shale. It's like the Marcellus shale. There's kind of Devonian organic carbon-rich units that kind of 7% or so organic carbon in it, which is a lot. And there's a section of Cretaceous OA from Morocco. That's a photo I actually found online, but that's another 10% organic matter or whatever. Rocks like this are the source of all the petroleum in the world. Rocks like this is why we have a modern economy. Whether we like that or not, that's basically what it is. And then this is coal trains in Virginia, right? So there's a lot of that too. So we bury carbon, we remove carbon from the ocean atmosphere system, either in the oxidized carbonate form, it's produced by weathering and then removed in the ocean primarily, mostly by biological activity, but we'll see you don't have to have that. If you didn't have shell-forming organisms, you'd still get there eventually. And also by the burial of organic matter. So trying to understand how much goes out as carbonate, how much goes out as organic matter is interesting from a number of standpoints. So anyway, talked a little bit about alteration of the oceanic crust. And it's hard to find really good graphics of this. In fact, this is a...
Do you have any idea of how the size of the carbonate reservoir compares to the buried organic carbon?
Yeah, we do. I'll come to that. We're a way of estimating how the inputs are, right? And so that's an important question. The oceanic crust is... So the last time I got invited to an ODP meeting, I pointed out that the entire history of DSTP and ODP with their 3-inch cores had sampled 1 part in 10 to the 13th of the ocean surface area. I haven't been invited back since. I don't really understand. So anyway, so we've got a problem, and sampling the altered oceanic crust is particularly difficult because of the alteration, core recovery is poor, all that kind of stuff. It's hard to get a complete section. There's only been a couple places where that's been done very well. Hole 504 is a famous one because Hubert Staudigl and Stan Hart figured that out in the 80s that there was decent recovery there. very seriously undersampled problem. So anything I say about alteration of the oceanic crust, take with a large grain of salt, because we just don't have enough data. But you get carbonate veining in there. You also get the addition of some organic carbon as well, which is even harder to see. Here's a micrograph that's 400 microns showing the alteration features, which I won't go through. I just was looking for something to show up there. But what Antigo had done, and some people have done a little bit since then, is to look at these few sections where there's decent thing here. And this came out. This is age in millions of years along this axis. And so the carbonate veins per square per meter of depth in the crust, or the carbonate content measured by reacting the rock with CO2 or by thermally decomposing it so you get the carbonate and the organic matter, increases with the age of the oceanic lithosphere. Okay? And the crust is warm, fluids circulate through that, not just at the mid-ocean ridge, but also off-axis lower temperature alteration. Again, not highly well constrained, but adds carbon to the crust with time. And so it turns out that that's a non-trivial amount of material. And I'll come back to that in a little bit. But I guess just keep that process in mind. And then the question is, how can we estimate the rate of CO2 degassing globally? Because you can't run around and sample all the volcanoes, and they're very uneven in time. Right now, Mount Etna or Vesuvius, one of those, has a huge CO2 flux out of it because there's some limestone blocks buried down there somewhere, they think. So you can't sample it well. So there's a couple ways to do that. One is just to look at the CO2 to helium-3 ratio in gases. Helium-3 only comes from the mantle. It's primordial. There's no radiogenic production of helium-3. So whatever helium-3 the Earth started with is all it has now. And helium-3 escapes from the atmosphere, right? So it's not held in the atmosphere like the other gases are. So there's a small amount of helium-3 in the atmosphere that's a steady state between the rate of degassing and the rate of escape to space. And so so people run around and measure the CO2 to helium-3 ratios in different kind of rocks, and then they get some estimate of the helium-3 flux because it only has this one source, and it doesn't accumulate. And so this is from Marti and Tolstekian, and there's been some estimate of this. And this somehow I managed to get screwed up just a little bit there. Anyways, so from that kind of estimate, you get something like 2 times 10 to the 12, or 2 teramoles of CO2 per year from Morbs, and most recent estimate from Dave Hilton and company is a little less than that from ARCS. And then the term that sort of fell off the bottom there is the plume flux is not so well known, right? And that could clearly, on a geologic time scale, if you get a big plume event and you erupt, the Siberian traps in 100,000 years or something like that, it's going to be a lot of CO2, which is not going to be captured by this. And there are other ways in ARC, sometimes people use the CO2 to sulfur dioxide estimate. Anyway, so these estimates are, they have uncertainties, but they are what they are, right? And so from these two sources, we're getting 3.5 to 4 teramoles a year. Maybe if we add plumes, we might get up to 6. We're not really sure about that. The plume term is not well known, and it's hard to really pin that one down. So here's back to the oceanic crust again, the same kind of thing, except showing the weight percent CO2 instead of carbonate veining and age. And Alton Teagle and other people have estimated around 2 teramoles a year of uptake of CO2 by alteration of the oceanic crust, right? So we're putting in fluids, which are reacting with the basalts and precipitating out as calcium carbonates. We'll also get some organic matter stored in the crust itself. So basically, that's within uncertainty balances the mid-ocean ridge degassing rate. And of course, there are significant uncertainties on both the degassing rate and the uptake rate, but that's what we know so far. So maybe the amount of CO2 production at the mid-ocean ridge, one scenario one could imagine is that, in general, the oceanic crust takes up what the mid-ocean ridge produces. And so it's generally approximately a net wash through Earth's history. That might not be true. All right, we don't know that even today well, and we certainly don't know that for sure if that's true in the past. Okay, so that's where the alteration of the oceanic crust is important, and that alteration is a function of crustal production rate, of the thermal history of the crust, and things that some of the people in this room know quite a lot about. And then it's also somewhat depends on ocean chemistry a little bit, we'll see. But I'm going to talk just a little bit about ocean chemistry because Thorsten really wanted me to, and it was sort of explain one or two things that I think we hit on last time just a little bit. So I'm going to switch gears for a second to think about what controls the removal of some of that CO2 as carbonate, and that will segue into what might happen to that stuff when it gets to the subduction zone, because that's sort of important, right? We sediment onto the oceanic crust, we move that into a subduction zone. And if I asked 20 different ones of you what happened then, you could probably give me 20 different viable stories, right? So it's an important question. So if you look at the chemistry of calcium carbonate in seawater, calcium carbonate is kind of unusual in that it becomes more soluble with decreasing temperature. Okay, most things become more soluble in hot water. Calcium carbonate goes the other way around. And that's because it's an entropy effect kind of thing. It doesn't really matter. It also gets more soluble with increasing pressure. And so if you look at surface seawater, and that dashed line is saturation with respect to calcite, that dashed line is saturation with respect to aragonite, another polymorph of calcium carbonate. And this is depth in the ocean. This is an old crummy figure, but excuse me. But the surface ocean is strongly supersaturated with calcium carbonate. So if you're an organism living in surface seawater, you're swimming around in an environment that's supersaturated by a factor of several with respect to calcium carbonate, and therefore you find it fairly convenient to tickle that supersaturation and overcome the kinetic barrier and make a house out of it, right? And interestingly enough, diatoms make their houses out of silica, which is undersaturated in surface seawater, and they have to work harder to do it. But they showed up a lot later in the evolutionary record. So the surface ocean is everywhere supersaturated with calcium carbonate. And if we didn't have any organisms that helped catalyze the precipitation of calcium carbonate, we'd supersaturate somewhat more, and then it would precipitate without being catalyzed biologically. But now almost all calcium carbonate precipitation in the ocean is catalyzed by organisms of one kind or another, diatoms, corals, you name it. So, not diatoms, excuse me, coccoliths. As we go deeper, the water gets colder. So that increases the solubility. The pressure gets greater. That increases the solubility. And also, because of the respiration of decaying organic matter, we add more CO2 to the deep water. It gets more acidic, and that increases the solubility of calcium carbonate. So at some depth, you cross from being supersaturated to undersaturated, right? And that's your lysocline or whatever. Your calcium. And so what we end up with is at deep parts of the ocean, we don't deposit calcium carbonate because the water is undersaturated with it. And in shallow parts of the ocean, we do. And then somewhere in the middle, we do or we don't. And that can vary over time, right? And that's sort of an important thing. And that gives us some history. Because if you think about the ocean, it contains a fair amount of calcium and a fair amount of dissolved CO2, about 10 millimoles per liter of calcium, about 2 millimoles per liter of CO2 in a dissolved form as bicarbonate or whatever. But it's still a finite reservoir. You put it into the oceans, and on a time scale of tens of thousands of years, what you put in you have to take out because it can't just continue to accumulate it because then it gets more and more saturated and comes out. So we can, on the time scales we're talking about, we can consider this at sort of steady state. So if we put more weathering products into the ocean, we should, all other things being equal, see that the depth to which we find calcium carbonate goes down, right? And so that's called the CCD, or the carbonate compensation depth. And here's a schematic from a good paper a couple of years ago. So here's the lysocline where you kind of go through saturation, but you still have material raining out. So the CCD is sort of what you observe. And if you go to rocks, if you go to sediment cores and you look for the CCD, you can see it because above the CCD where there's lots of calcium carbonate, the sediment is light colored, and below the CCD where there isn't very much carbonate, the sediment is dark colored. And Ben here can tell you about this in enormous detail, right? I'm not abusing it too badly, am I? No. And so you don't have to be, even a seismologist could recognize when he or she was above or below the CCD. Okay, so it's actually not too bad. It's white rocks versus brown rocks. Okay, this is all you got to know. And so. Anyway, and of course this can go up and down depending upon the calcium carbonate supply and the degree of undersaturation of the water. It's going to be a competition between how much calcium carbonate you're adding and how corrosive the water is, right? And the corrosiveness of the water is going to depend on PCO2. This is a complicated diagram, and what you want to do, yeah, it's a very complicated diagram. What I want you to do is, this is time through the Cenozoic. I'm sorry I got cut off a little bit here. I got to change the screen resolution. Oh, never mind. Okay, this is the Cenozoic here. I'll fill in the time scale for you. Those are all the crons. So, so anyway, these are reconstructions based on a bunch of different cores across the Pacific of the Cenozoic history of the carbonate compensation depth. All right, and the paleo depth here going from shallow to deep. All right. So the red jagged line here is the only one that you really need to pay attention to right now. This isn't my diagram. I guess when you're trying to write a paper in Nature and you've got 10 things to say, you put them all in the same diagram and hope the readers can figure it out eventually. And so anyways, so you can see back in the Eocene, Paleocene, the carbonate compensation depth was fairly deep, and fairly shallow, 3.5 kilometers in the Pacific. This is the Pacific. And then there's this big drop off here, and that corresponds pretty closely to the end of the Eocene, right? And do you remember exactly what cron that was at?
13N.
Yeah, so that's right there at around 30. Anyway, this corresponds approximately to when the glaciation of Antarctica and the beginning of the Oligocene. Okay? And so the fact that the carbonate compensation depth is getting deeper means that we're probably supplying more calcium carbonate to the ocean. And so that's causing the mean dissolution depth to become deeper because we're just shoveling it in faster, right? So it's dissolving, but we're shoveling it in faster, so we deepen the CCD. And
not as much water.
And not as much water. We've got also sea level drops with ice, and so then you don't have as much shelf area, right? Probably there's not a huge sea level drop at the onset of glaciation in Antarctica, but there's some, and of course it gets much worse as you go further into the late Cenozoic and get into the Pleistocene. You really have a problem with shelf area at the LGM, for example, right? But you began to lose some shelf area there. And so that's the 018 record. There's your first drop in 018 indicating the onset of glaciation in Antarctica. And that's ice volume mostly and a little bit of temperature, right? So there it is. Okay? So something is changing with weathering through this interval. And we're accumulating more calcium carbonate, which means we must be weathering more of it on land. And we end up cooling things off, and we make ice in Antarctica. And then it bounces around through the rest of the Cenozoic, and there's many stories to be told there, but I don't want to dwell on that. Oh.
Sorry, maybe you're going to talk about this, but how does this now, what is the relationship of those changes with spreading rate variations? Well, what do people think about that? And spreading rate variations will do at least two things, right? You can have different amounts of ice levels in relation to the ridge, different amounts of seafloor production, and then depending, we have curves that would predict the change of the seafloor distribution, which means the change of the volume of water.
Yeah. So yeah, thinking along these lines some years ago, I kind of put that to Dave Rowley, who then went on and reintegrated the area age curves for the seafloor. And his claim, and it's published, is that there's no change. The area age distribution, as far back as we have seafloor, is entirely consistent with a constant spreading rate since, the end of the Jurassic or whatever. Well, you're not the only one, right? So the question is, whose spreading rate curve should you believe? I'm sure yours is the one I should believe. But so I think that's a question you might be able to really address better than I can, right? So there are differences of opinion on this. And that's an important parameter, right? How does the spreading rate vary in time, or does it? And Rowley has argued that it doesn't, at least over the last 100 or 150 million years. And his data tell a story, right? But obviously, as you go further back in time, you have less and less of the seafloor to sample. So all he says is there's nothing about the data that are inconsistent with a constant spreading rate for the whole time that we have any seafloor at all.
Yeah, I mean, this is a long story. We could debate this. We think there are reasons why this is not a good argument.
Mm-hmm.
But what I'm saying is, have people tried to quantify the relationships between those kind of curves and whatever you might get from different hypotheses of variation in the spreading rate, where one hypothesis might just be constancy.
Yeah.
And I'm asking this sort of out of the blue, and I've been talking with people about this.
Yeah.
They said we should do this.
Yeah.
I'm always
No, I don't think so. This is relatively new. These curves are a major pain in the neck to compile. You've got to get all this. I mean, there's a huge amount of work that went into this diagram, right? And so it had been done back in the day by Turge Van Andel in the 1970s or something, and then there were a few things, updates on that. And nobody had the stomach to do it again until a couple of years ago. So, we were all citing this sort of hand-drawn sketch in Turge Van Andel's book from 1975 or something, and then some other things. And anyway, this is the first real attempt to update that. So I'm not sure that calculation has been done in the literature that I know of anyway. It would be interesting. Yeah. Well, the original argument for driving these models, like the Blagg-type models, was it was all driven by sea level curves. Okay, the old sea level curves on the idea that sea level went up and down if you didn't have glaciation just because of ridge inflation and deflation and all that kind of stuff. But a couple things happened. And one of them is that when people, and they were all sort of tied to the Vail curve or something like that. But then, the people like Ken Miller and all that kind of looked at that stuff and said that the amplitudes on these Vail curves are out to lunch. And so, anyway. So, but yes, the original Blagg models were all fundamentally driven by the sea level curve because that was the proxy for mid-ocean ridge production, which is also the proxy for subduction. So everything depended upon these sea level curves, right? But I don't think that was robust, but that's the way they did it, right? Back in 1983, it probably was a good idea. But it's not how you'd want to do it now. So this is important. How much this varies really does matter. Okay, and I'm a little agnostic about what the right answer is. I just, this is an issue of constraints, right?
It was also the time frame, too, because if you talk about acidification, it's only short time frames that are less than maybe 100,000 or 200,000 years. But if you're talking about buffering capacity and deepening as the CCD, if you have more carbon going into the system, then you're only talking really about long-term periods when the buffering can keep up with the source.
Yeah, and that's kind of what I'm focusing on is a longer-term picture here, because that's yes, you're right about that. And so anyway, this is the 018 record from Jim Zakos. There's your onset of Eocene Oligocene glaciation right there. There's the early Eocene climate optimum, etc. There's our Pleistocene with the big glacial and glacial variations, right? A lot of the noise here is ice volume, but this gradual, at least down to here, it was an ice volume, right? After there, it's a combination ice volume and temperature, and then it's mostly ice volume there because the ocean's already cold. You can't make it that much colder. The deep ocean, anyways. So anyway, these are some reconstructions, and there's updates on this from the PCO2 records. There's a lot of disagreement early on, but in the Eocene, most of the methods agree pretty high PCO2. And in the Oligocene onward, pretty low PCO2 with some noise around. There's better ones than this, but basically. And that would be consistent with weathering, drawing down CO2, deepening the CCD, and then CO2 bouncing around, 280, 350, 400 ppm in the last 25, 30 million years. The big change being back through there. So anyway, so in a sense, carbonate deposition is the smoking gun of weathering on land, right? We can talk about the polonium-bolonium isotope system, but if we see more carbonate in the oceans, it had to come from somewhere, and it had to come from the terrestrial surface, right? Whereas the polonium ratios may come from lots of things. So that's why it's nice to go back and look at the carbon records themselves rather than the tracers and see are they consistent, right? So anyway, so this is grossly inconsistent with the story from strontium isotopes. If the strontium isotope story was correct, we should see a big deepening of the CCD after about 24 million years, and the strontium isotope record really takes off, or after 16 million years when the osmium isotopes takes off, and we should see CO2 falling since the early Miocene. Doesn't look like it happens. Okay, and like I said, there's some updates on this, but it's not dramatically different. So okay. So we put calcium carbonate on the seafloor, but we don't put it everywhere in the seafloor. We put it down to 3-4 kilometers. Certainly in lots of places in the Pacific, the ocean's deeper than that, right? And so those deep Pacific basins don't have calcium carbonate on them. So the stuff that's being fed into the Philippine Trench or any of those deep trenches in the Western Pacific are essentially carbonate-free, whereas the stuff that's being fed into Barbados is not carbonate-free, right? The Atlantic is pretty well covered in calcium carbonate, the Pacific only some of. So what happens when it gets there? Okay, so this is a paper just from a couple years ago in that esteemed journal, G-Cubed, and So how many have we got? Most of the editors are in the room, right? Where's Jim? What's he doing? Anyways. So anyway, they did a budget on the amount of carbon coming in, just the sedimentary budget, essentially, coming in on the Cocos Plate. This is in Costa Rica. This is Hilton is the kind of the head, the ringleader of this group, Dave Hilton. And so they've got something like 1.6 times 10 to the 9 grams of carbon per kilometer of trench length coming into the system per year. And then they estimate, based on a bunch of measurements through the margins program, how much of that carbon is degassed in the forearc, outer, inner, and the volcanic front. That's 10 to the 9, that's 10 to the 5th, that's 10 to the 8. So they come up with, and they don't even try to account for the alteration of the igneous part of the oceanic crust. So they get a maximum of about 12% of the carbon brought in on the Cocos Plate comes back out the subduction zone, either in the forearc or in the volcanic front. So 12%, 10%, whatever. It's not a lot, right? So the rest of it has to go somewhere. Yes?
How can we be sure that the CO2 released by the volcanic front derived from mantle and not from, for example, crust already?
They're not even sure. They're saying all the CO2 out is only 10% of the CO2 coming in, and it could be from some other source, in which case it's even less, right? So yeah, they make some arguments where they think some of this is, out here at least it's from the sediments. Here, who knows, right? So at any rate, if this is even close to right, there's a bunch of carbon going down into the mantle somewhere, and what happens to it? All right, where's Rajdeep? He's going to explain this to us, right? Yeah. So, interesting set of observations. This is the best characterized arc system right now for this. Someone was asking me at lunch about whether we could make a comparison really on an arc-specific basis of weathering uptake of CO2 versus degassing. Unfortunately, the places where we have the best data on degassing are not places where we have any information on weathering and vice versa. So we can't really do that yet. It's an understudied problem. But this is, if this diagram is even close to being right, this is a big deal. Okay, some people have argued, Dan Schrag in particular, have argued that if you put carbonate on the seafloor, put more carbonate on the seafloor, and you subduct it more, then you can have more CO2 coming out of the arc, right? And maybe not. This doesn't support that very well. The other issue I think that Jerry Dickens raised by email prior to this is that those warm periods when we might have had more arc degassing to get the CO2 higher, this is when you saw the CCD was relatively shallow. The deep oceans would be more acidic because CO2 would be higher. It would be harder to put sedimentary carbon down in an arc under those conditions, right? And so, anyway, this remains a big source of. There's a long way to go to fully understand this.
Are there studies that do this in different places that have different heat losses?
So there are a number of them, and some of them are compiled in this very paper, and with more or less degrees of competence, right? What these guys say is that pretty much everywhere that they know of data, this is roughly the story you see, except in a couple of places like Japan, where maybe they're more close to being equal. But they say most of the arcs that there are data from appear to look something like this. This just happens to be the best characterized one.
So it does scale, but it's always about 10%.
Well, it's unclear because I'm not sure that the data are really good enough to say that there's a 10% rule. Okay, so that this is a data deficient problem, right? So it would be interesting if it was the 10% rule applied, right, in general, and maybe it does, right? But I think it's not something you could go to the bank on yet.
And you can't do convergence rate via CO2 out correlations, right?
It's not obvious. I mean, the composition of sediments being brought to the trench varies globally depending where you are. There's terreplankton gloss, and that's an average, but it varies depending where you are. And of course, the really deep ones don't have a lot of carbonate, and some of the shallow ones do. And so the idea was maybe there's a big relationship between how much carbon is introduced in the trench and how much carbon comes out. That's all I'll say, right? And I think there are people who know those details better than I do, but yeah.
One quick point. The fact that you were mentioning that when the CCD is relatively shallow, you can't have a lot of calcium carbonate sedimentation, but that doesn't mean the igneous part of the crust doesn't have carbonate.
Yes, that is correct. The igneous part of the crust should still be altered, and possibly may even have more carbonate in it if the temperature of the deep water is higher. So that's something that
You were only talking about the.
I was only talking about the sedimentary part. Of course, you have more in the sediments, but you're right. The alteration of the oceanic crust probably continues just as well, and maybe even a little bit faster under those kind of conditions. Yes, that is correct. So, okay, a couple things. So, sedimentary sinks. Okay, here's a couple ways of thinking about it. The global sediment flux prior to the anthropogenic perturbations has been estimated pretty well by James Fitzke and company at about 14 billion tons a year. Okay, something like that. The carbonate burial flux, based on sort of longer-term estimates, both from sediment inventories and modern ribbon chemistry, is around 24 teramoles, 10 to the 12 moles per year. On the long term, we expect weathering and carbonate sedimentation to be in an approximate steady state. So how do we estimate the organic carbon burial flux, which is a question that was raised a little bit. And you can do this with stable isotopes, because it's hard to go out there and inventory. The inventory methods are both tedious, expensive, and don't work very well because there's so much variation, right? So so you like something to do that more globally. So the basic idea is the carbon flux to sediments is composed of the carbonate burial and the organic carbon burial. And the isotopic composition of carbonates and organic carbon are essentially related by the photosynthetic fractionation with a couple of tweaks in there. And so we can write out an isotopic mass balance that the input to the system, which is volcanic CO2 ultimately, should be equal to the output. And the output is the fraction of organic carbon times its isotopic composition times the fraction of carbonate carbon times its isotopic composition. And of course, you can reduce that. So then you can solve that system for the stable, steady-state isotopic mass balance. And you get something like this, right? Well, that's sort of the photosynthetic fractionation, not exactly, but approximately. That's the mass fraction of organic carbon burial. So we know the isotopic composition of carbonate at any time. We know the input is from the mantle. And this varies. The photosynthetic and diagenetic effects vary some. But anyway, so that's what it looks like. Let's say you got +1 in carbonates, -5.5 coming out of the mantle. Fractionation is about 27. That gives you something on the order of organic carbon burial is 20-25% of carbonate burial. And that varies in time, right? We don't expect that to be constant in time. And so that's going to imply something like 6 teramoles a year of organic carbon burial if carbonate carbon is about 24. All right? And so this is kind of these diagrams are messy, but it's not as bad as this. But anyway, this is the isotopic composition of carbon and carbonate fossils through the Phanerozoic. You can see there's big variations. You know, there's sort of best estimate 95%, 90% confidence intervals. This is through the whole Precambrian, and of course the older stuff you have big problems with alteration. But there are also some weird and wonderful things that happen in the Precambrian. So anyway, but let's say here you go to here's the Carboniferous. You have high values of carbonate, of the isotopes in carbonates, and if you go back one, right, if that number gets bigger, this mass fraction gets bigger, and then you say, oh yeah, those are the coal swamps, right? So it correlates with some things we actually see. So it's a way of estimating the partitioning. When you remove carbon in the sedimentary record, how much of it is in the reduced form and how much it is in the oxidized form. Okay. What happens when you bury organic carbon? Well, it turns out you do a few things. You take CO2 and water, put some nutrients and some sunlight, and you make, in this case, this is a simple sugar, and you make oxygen, right? So for every CO2 you reduce, you release one oxygen. So that's the source of oxygen to the surface environment. The only other source is photochemistry, and that's trivially small in comparison. And so in a normal, in the short-term carbon cycle, you know, the fast stuff, that plants make carbon compounds, we eat them, and we run this reaction in reverse. And plants run this reaction in reverse too, right? And so most of the carbon, there's a large amount of carbon taken up every year, 100 and something teramoles, and 100 and something teramoles is returned by respiration, right? So it's almost a wash. But there's a small amount gets buried, you know, a few teramoles gets buried, right? And so this O2 is produced. What happens to it? Well, it can oxidize old sedimentary carbon, kerogens. Like if you've got an outcrop containing coal in it in Pennsylvania, that's going to weather and oxidize. It's going to consume. It's going to close the loop. You're going to oxidize iron and sulfur and reduce gases from the mantle and crust. It's primarily iron we're worried about because that's what most of the redox capacity of the mantle is, because iron is much more abundant than sulfur in the mantle. Or it can accumulate in the atmosphere. And apparently it did, and that's why we're here, right? So another question I want to pose as a thing to this group is it turns out that the oxidation of the oceanic crust, in other words, a different kind of weathering, rather than weathering about carbonate, we're talking about weathering iron and sulfur with oxidizing agents. And even if it's not oxygen is the proximal agent, it's tied to the amount of oxygen in the atmosphere, like sulfate, for example. That's going to be related. So here are a couple estimates. This is Lecoyer and Ricard, and they estimated the iron-3 to total iron ratio of 0.07 in the mid-ocean ridge. Back and Edwards estimated a value about twice as high, but they were really talking about just the upper 500 meters. They both find from ODP data that with time, that oceanic crust is oxidized as it gets older, and they end up with old crust. In both cases, increasing by about a factor of 3, but here it's from 15 to 45%, and here it's from 7 to 22%. And so you've increased the amount of iron. So you haven't oxidized all the iron in the ocean crust, but you've oxidized more of it. And depending on what you choose for the iron content of the crust and the production rate at the mid-ocean ridge, which is what Torsten was saying about, get a little bit of sulfur. So you imply an oxygen consumption rate just from oxidizing the oceanic crust of, let's say, about a teramole a year. But we produce about 6, right? So about 15%, roughly, don't hold me to these numbers in any great way, of the oxygen that's produced by burial of organic carbon each year isn't available to reoxidize old organic carbon, and it's already sucked off by the oceanic crust, right? So you've already got a problem. Your expenses are exceeding your income here, right? And students understand this issue, right? So anyway, it's a kind of a tax on there, right? And we can also do the continental crust, and we get about 0.6 teramoles a year for that, because the continent has reduced iron in it, not as much as the oceanic crust. It erodes. It has some reduced sulfur in it. These numbers are not extremely well known. I was bugging Roberta about these spring, but anyway, it gives us an idea. So we got about 6 going out. We got 1.7 that we can't account for. We got about 4.3 left. So at most, about 70% of the organic matter that we bury can then be reoxidized, because the rest of the oxygen needed to do that has been consumed by altering the crust, right? The non-carbon part of the crust. So, and also the residence time for oxygen in the atmosphere is around the order of 6 million years or so relative to these processes. So in the short term, we can imagine deviations for this. But if we're going to look at, geologic timescales, over the Phanerozoic, the atmospheric oxygen content has buried less than a factor of 2. We know that from animals. Prior to that, that's not the case. But so, we're gonna quasi steady state this problem. That's what you do when you don't know how to do it right. So anyway, here's a picture of weathering of an organic carbon-rich outcrop today. Right. So there's unweathered Devonian shale with a lot of organic carbon. One of these carbon-rich sediments. Its equivalent is the source of the gas in the Marcellus that everybody's up in arms about in my part of the country, and then that's where it's been weathered. And then they built a road cut through there a few years ago, so they've got this unweathered stuff. So clearly organic carbon is oxidized, and there are bacteria who can eat this dead kerogen. There are bacteria that have no carbon-14 in this outcrop because they're happily munching on Devonian carbon. That's kind of an interesting thing that Steve Petch and his colleagues found out about. But if you have less oxygen in the atmosphere, you might not even get that, right? And so there's a number of things that control the oxidation, the reoxidation rate of organic carbon. One of them is our old buddy mineral surface area. It turns out when you look at organic carbon in marine sediments and to a certain extent in soils, there's a very strong correlation. And this is my former postdoc, Martin Kennedy. He always does things different. He puts the dependent variable, there, right? This is Martin. But Martin's a smart guy. He's just different. And anyway, and I had nothing to do with this paper. I was not on it. I wish I had been. It's a good paper. But you see this a lot, where the mineral surface area, as estimated by some sort of gas absorption technique or something like that, correlates quite well with organic carbon. And the belief among the organic geochemistry community is the sorption onto mineral surfaces helps inhibit bacterial activity and other decomposing and things, and that actually helps stabilize the organic carbon over long periods. So mineral surface area is created during weathering. So now we tie the organic carbon cycle to the fact that weathering of rocks makes clays with high mineral surface area. So most of the ocean anoxic events. In the Cretaceous, for example, that organic carbon is associated with fairly weathered clays. So probably part of what creates those organic carbon-rich deposits, which underlie the Gulf Coast and the Middle East and fuel our modern economy, probably is the fact that clay mineral production is part of the story there. So that's one thing there that matters, right? So then it turns out the problem is even worse than I stated, because we make this oxygen, but we want to be able to reoxidize the old organic matter, right? But we can't oxidize it all because some of it gets taxed off by the iron and sulfur in the crust, right? But it turns out that we wrote that sort of photosynthetic reaction, CO2 plus water makes sugar, and then sugar plus oxygen, makes sugar plus oxygen, and oxygen plus sugar when you have lunch goes back and makes CO2 and water, right? But that's the way you always see it represented. But it turns out that's, like most things that are simple, is not true. And there are a number of reasons of that. But it sort of boils down to something like this, okay? Like I said, don't write this down, this is wrong. But roughly speaking, you get decarboxylation reactions, a part of biosynthesis, because the organisms have to produce a range of compounds from these primary sugars, right? No, we're not all made of sugar, as sweet as some of you are. It's a little more complicated than that. And so they make more reduced compounds. And so, for example, instead of that's got a 1-to-1 carbon to oxygen ratio, that glucose molecule. But after decarboxylation, driving off CO2, it now has essentially zero oxygen and still has hydrogen. So we've kind of made we've made cyclopropane, which is not actually. Never mind this. All right, forget that one. And also during diagenesis, you get the same kind of thing. So now instead of if I run that first reaction in reverse, glucose, oxygen goes to CO2 and water. 1 oxygen per carbon is all that's needed. But if I take one of these more reduced alkanes and do that, I need 1.5 oxygens per carbon. So I need more oxygen per carbon to oxidize it than I produced by producing it in the first place because of these decarboxylation reactions. And it gets it gets worse than that. So anyway, we can go on like that and produce these alkanes, which are basically what's in petroleum. And then you'll leave behind, and also you can drive off methane as part of this, and you'll leave behind some sort of graphitic carbon as an ultimate residue. And graphite is nature's Teflon. The stuff is inert as hell. The only data I could even find on the kinetics of the oxidation of graphite was reactor-grade graphite at like 500 degrees C in nuclear reactors, right? Because otherwise it's just inert as hell. And it seems to stay there approximately forever. So we make some reduced and defunctionalized inert carbon, and that apparently is stored in the crust for a very long time. And how long is very long? Maybe billions of years, right? And so we produce CO2 and methane. As that methane is very reduced. We get methane. I showed you pictures of methane seeps in the very first slide coming out of the ocean and sedimentary basins. The thermal degradation of organic. There are bugs that make methane, but once you get too hot for the bugs, thermal decomposition of this kind of stuff makes methane as well. And that's the source of most of the methane in petroleum basins is thermal decomposition. So anyway, so we now we have this issue that we've got to oxidize the oceanic crust, which is a tax on carbon. We have to oxidize these very reduced carbon compounds, which are more reduced than we made, so we come out ahead. It's like changing money. When you change money, you never get as much back. There's always some that's raked off the top, right? And so it's actually pretty serious. And so we've got a bunch of parameters to play with. We don't really know them all that well in order to do this, because we don't know exactly how much carbon is in the altered oceanic crust. We don't know exactly how the isotopic fractionations have varied, la-da-da-da-da. Okay, so, but you can at least kind of get an idea of what the available space might be. And this is, I'm just going to switch to I don't know how to add this to my PowerPoint. So it should come up in a second, I hope. There it is, okay. So I didn't know how to put something dynamic in MATLAB into PowerPoint. But this is, essentially what I've done here is look at a lot of different parameters and said, all right, I don't know what they all are, but I'm just going to Monte Carlo this thing. That's when you don't know what else to do. You do it by Monte Carlo, right? And so anyway, this is the fraction of organic carbon that's recycled here. In other words, all old organic carbon is reoxidized, none is. That's the fraction of carbon that leaves is organic matter, and that's the methane flux. I can do this in different parameter space. I'll just show you what this looks like. It's a pseudo plane, right? And so you can see, I just sort of fit this surface with it just to give an idea. The fitting of the surface doesn't mean anything. It's just showing you that sort of a pseudo plane in this space. And the idea is basically, I should probably prop this back up here or something like that. If I have a big methane flux, right, I've got to oxidize that really reduced carbon, so I must have a very inefficient recycling. In other words, I have to add a lot of carbon to the crust and store it so I can keep the oxygen available to oxidize the methane. Because the methane oxidizes fast. Right? It goes in the ocean and atmosphere and it oxidizes fast. It doesn't oxidize directly with O2, but ultimately it's tied to O2. So methane gets quickly oxidized, but the kerogens, the old stuff in the outcrop, doesn't. So what this says is we must be adding carbon to the crust over time to balance this net oxygen demand. Right? And when you do that, and you come up with some number like this, okay, and you look at it, you say, all right, let's start that around 2.5 billion years ago, because that's a nice round number. And when you integrate that forward for about 2.5 billion years, you come up with a number that's in satisfactory agreement with the amount of carbon that you estimate stored in the crust from Guo's data. Is that how you say his name, Bill? Guo? The guy that Roberta worked with on the composition of the crust. Gao. Okay, sorry. Yeah. So anyway, a lot of times people treat this as a steady state problem that carbon burial is equal to carbon oxidation. That's manifestly not true. And the reason, if we even want to maintain the amount of oxygen we have in the atmosphere now, because the oceanic crust is always trying to drag it away, we have to continue to add reduced carbon to the crust over Earth history. And my belief is, and there's some evidence of that much of that is in the form of this kind of graphitized, very unreactive carbon where the reactive functional groups have been knocked off and you end up with this kind of inert stuff, right? And we can put graphite little crucibles in our muffle furnace at 1,000 degrees for an hour and they come out and they're still graphite. They didn't catch on fire at 1,000 degrees centigrade, right? So anyway, that's kind of some considerations of when we start thinking about the carbon cycle, we have to worry about the carbon budgets. Right? We have to worry about the isotopic budgets. It's also coupled to these things like oxygen, carbon, iron, and sulfur, and we have to think about those too. So there's a lot of constraints, but there's also a lot of unknowns. So it gives you some sense of kind of how this works on a long time scale. On short time scales, we can clearly have deviations, right? Because the steady state response time scale for CO2 is an order of 500,000 years. The response time scale for oxygen is an order of a few million years. So at a shorter time scales than that, we can get variation. No reason why we shouldn't. But on these longer time scales, we've got some issues. And of course, it is widely believed, and there's even evidence of this, although it's partly a matter of belief, that the oxygen content of the atmosphere changed, possibly in 2 steps, maybe from 0 to very little about 2.4 billion years ago, and from not very much to something like the modern value about 600 million years ago. That latter history is not very well constrained, but we would like to know that, right? And is there a relation between these geodynamic processes that might create conditions where we can get an excess burial of organic matter, not merely enough to satisfy the tax man, but to actually come out ahead, right? You sort of feel like you work hard all day and you pay your taxes and you pay your rent, you don't have any money left. That's the carbon cycle today. Okay, you want one of those intervals where you're actually, putting money in the bank, right? And that has apparently happened a couple times through Earth history, but it seems to be the exception rather than the rule, that you're constantly having to pay the tax man, and that sort of takes away your profit. So, yeah, that's my Tea Party talk for the day, right? Okay, so I'd be happy to answer some questions about this. I don't want to go on too long because it's Friday afternoon. It's been a long week. It's been fun, but this is a little bit of a different view. So there's some really. The reason I sort of focused on this is what happens with the alteration of the oceanic crust, both from a carbonate standpoint and from an oxidation standpoint. And then what happens when that stuff gets to the trench are big uncertainties that could really change the picture here, not just a little bit, but change it a lot. And also what Thorsten mentioned, how does the production, the accretion rate of ocean crust and subduction rate, how does that vary in time? Right? Is Dave Rowley right or not? And so some of you are much better equipped than I am to address those questions fruitfully. And I think this is interesting because there are obvious geodynamic implications, but it turns out there are big implications for the exogenic or surface environment as well. So any questions about this? And don't be afraid to ask a dumb question, because that's how you learn any. If you already know the answer, you're not learning anything, right? Dumb questions are actually pretty good. Gotta ask some of those. Or is all perfectly clear? Cynthia.
So the organic carbon, so I guess the Costa Rican thing that you showed, is it mostly carbonates, or is there some organic carbon?
There's some of both there. And I think there is carbonate on that margin, right? That plate's relatively young there, so it's not that deep. And I don't know, some of you may know.
It's mostly carbonates, actually.
Yeah, mostly carbonates, yeah. So it's a young and not very deep plate, so it's got plenty of carbonate sedimentation on it. So the early prediction was there should be a lot of CO2 coming out. A lot of that CO2 should be decarbonated at some point in the subduction zone. It should come out of the volcano. It's not clear that it does that. And the gentleman your colleague sitting behind you is going to explain to us why next week, right? So, yes. Well, that's what I meant. A couple, yeah. I said gentlemen. You're excluded.
Oh, since you say that, let me ask you a question. It might be a little out of your wheelhouse, but you brought it up. It does relate to the Rowley and the sea level curves. And okay, if we say Vail is out of whack in terms of amplitude, Hack is out of whack in terms of amplitude, is there anybody I can believe?
I think you can believe Ken Miller. They put a lot of work onto this, but they really only go back, maybe 50 million years or something like that. But they put a great deal of effort into trying to calibrate that on the New Jersey margin and other places. But there's still the issue of sort of the geodynamic, buoyancy effects, right? That cause, speaking of Dave Rowley, there's a new paper out there, about the eastern margin of the U.S. and how that's gone up and down with the Farallon plate. You've seen that, right? So I think there's still, to answer sea level is obviously a really hard thing to get at. People used to think there was a dipstick, that there was some place in the world where you could measure sea level. And it's pretty clear that no such thing exists. And so, really doing sea level right requires very careful stratigraphy and backstripping and all that kind of stuff, and coupling to sort of a global 3D geodynamic model, right? So Jerry Mitrovica has been involved in this some, but I think, the story is not over. But it's pretty clear that the Hack-Vail stuff is just not quantitatively. They have the timing about right, but the magnitudes are not sensible.